relation to solar photovoltaic to the power grid. In a time where the world is on the verge of an economic crisis, it is really important to pay attention to renewable energy sources and ways to enhance their efficiency. In order to enlighten us on this topic, we have an outstanding personality here with us today. Let me take the pleasure of introducing our guest speaker for the evening, Professor Udaya Annakkage. Being an alumnus of the Department of Electrical Engineering at University of Moratuwa, he received his MSc and PhD degrees from the University of Manchester. He currently serves as a professor at the University of Manitoba in Canada and also as a professional engineer in the province of Manitoba. Professor Annakkage has more than 30 years of experience in lecturing, research, and consulting. His main research interest is in the area of power system stability. He is responsible for supervising a number of MSc and PhD students at the University of Manitoba in Canada and at the University of Auckland in New Zealand. He was appointed as the head of Electrical and Computer Engineering Department at the University of Manitoba from 2008 to 2012. He is a remarkable member of IEEE. While he has served on several working groups in IEEE, he also contributed to the organization as an editor of IEEE Transactions on Power Systems from 2009 to 2012. Sir, it is an honor to have you here with us today. I'm sure your vast knowledge on the subject matter will help everyone who's joining with us immensely. Over to you, sir.
Thank you very much for that introduction. First of all, I would like to thank IEEE Student Branch at the University of Moratuwa for inviting me to deliver this webinar. And this invitation is very special to me because as mentioned in the introduction, I obtained my undergraduate degree from the University of Moratuwa almost 40 years ago. The topic of integration of solar photovoltaic power grid, I chose this topic not only because Sri Lanka can benefit from this technology, but also, and most importantly, I believe there's potential in Sri Lanka to contribute to the advancement of technology. So in my presentation, I'm going to touch on global trends in solar photovoltaic. Briefly, I will talk about how the solar PV cell work, and I will move on to the PV cell electrical characteristics. Then I will talk about what we need for large-scale solar power plants and some concepts of controlling those large-scale solar power plants. Then I will introduce, again very briefly, converter technology. From that, I will move on to the challenges of interconnecting solar PV into a power grid. And finally, I would like to present a new control technique that we came up with within our research group. Okay. So in this slide, I'm showing two graphs. One is a bar chart and the other one is a line graph. The bar chart the total solar PV installation globally, and you can see there's a steady growth in solar PV installations over the past 10 years. The line graph shows the number of gigawatt scale solar power plants. It shows a percentage of top 10 out of all large-scale solar power plants. So the decrease in number shows there are more and more very large-scale solar power plants being installed around the globe. Now, what's the reason for this? One reason is the demand for clean energy and environmental concerns, and of course, high energy demands. So that's the politically driven aspect of the driver for growth in solar PV installations. On the other hand, from the technical front, the cost of PV cells has gone down and is still going down, and also increase in efficiency. So these drivers contributed to the growth of very large multi-megawatt solar power plants installed around the globe. Now, let's see solar energy resource. The amount of solar energy that falls on the surface of the Earth is estimated to be around 6,000 times our total energy demand. So this is a huge amount of energy. And of course, we can't convert all that energy to electricity. There's no need to do that. And also converting all that means you're covering the entire surface of the Earth with solar panels. And also the amount of energy that we can convert depends on the efficiency of energy conversion and atmospheric conditions. But still, this is a huge amount of energy that we can tap into. The concept is a photon with high enough energy can cause an electron in a photovoltaic material to break free of the atom so that the electron can freely move, completing a path across a load, essentially driving a current into a load. The energy in the photon must be at least equal to the band gap energy of the material, and this band gap energy can change from one material to another. And the maximum theoretical efficiency of conversion of solar energy to electricity depends on two things, mainly the material, or in other words, the band gap energy of that material, and the distribution of energy in the solar spectrum. For a given material, the conversion can take place only within a certain band of energy in terms of wavelength of the energy. Now, how does a PV cell work? It's essentially a PN junction, like a diode. And we know in a diode, the zone where the P-type material and N-type material meet, we have what we call depletion area. In the depletion area, we have a large electric field. Now, when a photon is absorbed by an atom with certain probability, it will release an electron from the atom, creating a whole electron pair, and the electric field in the depletion area will push holes into the P side of the PN junction and electrons into the N side of the PN junction. So the accumulation of electrons on the N-type material and holes in the P-type create, in terms of electric circuits, creates a current source. And the strength of the current source depends on the intensity of radiation of energy and also various atmospheric conditions and the photovoltaic material itself. So in this diagram, we see an external load is connected. It shows a resistor connected between P and N-type material of the PV cell. So with the load connected, the electrons accumulated in the N-type material can flow through the resistor to the P side, and electrons combining with the holes. That creates a current through the load. And the current going through the external resistor will create a voltage. So in terms of electrical characteristics, we can idealize this cell uh, in a very simple way. We can idealize this into two components. One is a current source, the current generated by the photovoltaic action, and the diode, because we have PN junction. So we can characterize a PV cell in a very ideal manner with the current source shown as IG and the diode current. Because when there's a current and that current drives a load, there is a voltage, and that voltage will forward bias the diode. So we'll have the forward bias characteristics of the diode, and the current available to the load is the difference between the photovoltaic current generated minus the diode current. So to the right of this slide, we have put those characteristics in an equation. So first component is the photovoltaic current, which is constant for a given level of irradiation and atmospheric conditions. And then we have the diode current, and we know the diode current characteristic is non-linear with respect to voltage. And in fact, the diode current increases exponentially as the voltage increases. So at low voltages, the current available to the load is almost equal to the photovoltaic current generated. But as the voltage increases, the diode current develops. And if the diode current is equal to the photovoltaic current generated, then the net current available to the load is zero. Now we are interested in extracting electrical power from the cell. And the electrical power is the product of voltage and current. So if we look at this, the voltage current characteristics of the load, uh, with zero voltage, we have the largest current, but we can't generate any active power because the power is the product of voltage and current. And then as the voltage increases, the diode current rapidly increases and the net current goes down to zero. And that's when the voltage is highest in these characteristics. And with highest voltage and zero current, again, we can't generate any active power. So the active power available changes from zero at zero voltage to it goes to a peak and then again zero at zero current. A more realistic electric circuit for the solar cell, we can include the effect of conducting current with a shunt resistor. And also there's a small voltage drop when we deliver a current from solar cell. We can model that voltage drop using a small series resistance. So we have simply added a parallel resistor and a series resistor to the ideal electric circuit of the solar cell. Now with this electric circuit, and I have not shown in this slide equation for the photovoltaic current generated and the diode current equation, you can combine those characteristic equations and obtain the characteristics of this circuit. We have 4 graphs shown. The top 2 shows power versus voltage. On the left, you have power versus voltage under different temperatures, and on the right, power versus voltage under different irradiation conditions. We can see that the maximum power that we can extract from the cell decreases as the temperature increases, the peak power decreases, and with increased level of irradiance, of course, we would expect more power available. So we can see the peak power increases. Now, one thing very important to note is the peak power doesn't happen at the same voltage. Depending on the temperature and depending on the irradiance, the voltage of the PV cell that gives the maximum power changes. So one of the task of optimum operation of solar system is to track this maximum power. The bottom two curves again shows the effect of temperature and the level of irradiance uh, on the current versus voltage characteristics. So with increased levels of temperature, the point at which the current starts falling uh, moves to left, and with increased level of irradiance, uh, the photovoltaic current generated increases. Now, when we are talking about large scale or any practical useful level of voltages and currents, we have to combine cells. So this slide shows how cells are connected in series to create a module. So in this diagram, we have 72 cells connected in series to create one module. And depending on the voltage you need, you can combine several modules in series to create a panel, and then several panels connected in series to get an array of solar cells. For example, using some typical values for silicon photovoltaic material with a module made up of 72 cells and some typical RP and RS values of 10 ohm and 0.001 ohm and reverse saturation current of 0.5 amperes. And under standard atmospheric conditions and standard solar radiation levels, a short circuit current of 6 amperes. You can use those equations and the electric circuit of the solar cell, so in this case, the module, to show that maximum power point is approximately 40 volt, and the power you get from the module is around 240 volt. So we can see if you want to get scale this up to operating levels, say for grid operation, you need many of these modules in series to get the correct voltage level and connect them in parallel to get the desired rated current. So this slide shows some topologies of connection of solar panels. The diagram A is what's called central inverter type topology, where we have connected solar panels in series to make a string, and then number of strings in parallel. So with parallel connection of strings, you can get the rated current up to the desired levels. With series connection, you can bring the voltage up to the desired level. Diagram B, we have inverter for each PV string, and with that we get a lot more flexibility than the central inverter in terms of tracking the maximum power point that we discussed earlier. But it turns out that the cost of the inverters is much higher compared to the central inverter. Although the central inverter, the rating is higher, multi-string, we have several smaller inverters, but the total cost turns out to be much higher when you have multi-string inverters. Figure C shows what's called module integrated structure. Now, for large scale integration of solar, the most preferred topology is topology A, which is with central inverter. One thing I did not touch on in explaining the operation of solar cells is the effect of shading. If one of the cells or module is shaded, it has a huge detrimental effect on the available maximum power transfer. So when a cell or a panel is shaded, you have to bypass using a diode. You can bypass each panel using bypass diode, so you can group panels and each group can be bypassed. And also, as you can see in the diagram, each string also has a diode to bypass one string when there are defects on any of the components. Now, just to give some practical numbers, with strings, you can go up to 2 kilowatt, and typically interface is single phase. Multi-string can go up to about 6 kilowatts with interface single phase or 3-phase, and centralized you can go into megawatt scale solar power plants. Now, I must mention this. I always encourage everybody to use the terms power plants and wind power plants instead of solar farms and wind farms, because these are just power plants, just like thermal power plants and hydropower plants. They are power plants. So I use the terminology solar power plants and wind power plants. Okay, now let me just touch on maximum power point tracking. There are various algorithms. You can find hundreds of papers. My slide is moving. Can you go up? One of the concepts is what's called perturb and observe. Essentially, we calculate the output power, and then if you see what happens if you increase the voltage by a small amount. If power increases, in the next cycle, you increase again by a small amount. Or if power decreases, you decrease the voltage by a small amount and keep doing that. So that gives you the maximum power point voltage. So the simple control block diagram at high level is shown here. You measure voltage and current, and the maximum power point tracking algorithm will tell you the ideal voltage, and you compare that ideal voltage with actual voltage, and then we come up with ID reference. ID is the component of current in phase with the grid voltage, AC side of the inverter, and IQ is the quadrature component. So the PPV controller comes up with the desired reference current. And if you also want to control the voltage or reactive power, you can come up with IQ reference. And then it goes into EQ frame current control to come up with the desired voltage waveform, to synthesize the voltage waveform. Now the question is, when we talk about ID reference, IQ reference, as I said, ID is the in-phase component of the current. You have to synchronize this to the grid to determine the phase angle. So we can synchronize using a phase lock loop. Again, there are many different phase lock loop approaches published in literature. And the one I have shown on this slide is what's used in PSCAD, taken from PSCAD user manual. So the input to the phase lock loop are instantaneous voltages of phase A, B, and C of the AC side of the converter. And we do the Park transformation as shown in these equations to get VD and VQ. From that, we can get the angle, inverse tan VQ divided by VD. So this is just one way of getting the converter synchronized to the grid. And what's something that's very important is we have to make sure that the phase lock loop is stable under operating conditions of the solar power plant. For that, you have to tune the proportional and integral gains, and this is actually very challenging task, especially when the solar power plant is connected to a V grid. Now, to synthesize this waveform, there are different ways using voltage source converters. The simplest technology is what's called two-level voltage source converter. The disadvantage of two-level is it introduces a lot of harmonics and the switching losses are very high. You can improve the harmonic situation and losses by moving into multi-level voltage source converters. And the modern technology and I believe is the technology for large-scale solar photovoltaic integration to grid is what's called modular multi-level topology or MMC. I think given the time, I have already used about 25 minutes. I will rush through these slides because I want some time to get into the new technology that we are proposing. So two-level converter, essentially these are IGBTs with antiparallel diodes and can be considered as a switch that can be switched on or off at any desired time. So by placing VD over 2 or negative value of VD over 2 at these AC nodes. So with that, we can synthesize the waveform. So this shows different stages of switching. Figure A shows upper switch is closed, the lower one is open. And then figure B is the commutation. When the upper switch is switched off, current continues through the antiparallel diode, and then the current continues through that with upper switch being off. So with this, you can get a square wave, as you can see in the various diagrams from A to E here. And if you appropriately control the duration of positive VD over 2 and negative VD over 2, we can get a waveform, something that looks like the one shown in this slide. And the low frequency component of this waveform is a sinusoidal waveform with proper control of the width of these pulses. So if we can filter all the high frequency components out from this waveform, you can get the sinusoidal waveform. Then multi-level ESC, and let me move on to MMC because that's what we need for large-scale solar PV integration. This technology was introduced early, about 20 years ago. And as the name implies, it's based on building blocks known as submodules. Advantages are the modularity, scalability. You can add modules in series or in parallel. and improve the harmonic properties. And if you have enough number of modules or submodules, you can create almost smooth sinusoidal waveform. And when you do that, you don't need filters. And reduce losses and redundancy are the advantages. So the submodules can be half bridge or full bridge. With a half bridge submodule, you can insert uh, the voltage across a capacitor, or you can bypass. When you bypass, you insert zero voltage or you insert plus VC. With full bridge, you can bypass getting zero, or you can insert the capacitor voltage, or you can insert the opposite capacitor with opposite polarity to get negative value of VC. Of course, full bridge is more expensive because it involves more components, but the advantage of full bridge is if there's a fault on the DC side, you can block the DC fault current when you have full bridge. So MMC is, so this diagram shows a three-phase MMC with half bridge submodules. Just to touch on some terminology, a cell string, we can add modules and create a cell string or stack. We have three legs, face legs. We also have what we call arm inductor. An arm inductor has a number of purposes, absorb any difference in voltage inserted by the two-phase stacks, provide the first layer of protection against fault currents, and lower the rate of rise of fault current because of the inductive effect. So in each phase arm, we can, by proper switching, you can insert all the half modules in series. That means adding all the capacitor voltage, or you can insert any desired number of capacitors through proper switching. So this diagram shows how to create a stepwise voltage waveform with the strings. The diagram shows n number of half bridge submodules. So obviously, if we insert all the capacitor voltages, then the voltage across the string is sum of all the VCs. And if all the capacitors are charged to the same level, you can get n times VC. If you bypass one of them, you get the next level down and so on. So if you have enough number of submodules in series, you can craft a very smooth waveform. So this is the same thing with full bridge. Okay, now I want to move into the next challenge. So we know how to track the maximum power point of the solar plant, and we know how to synthesize the waveform to achieve that maximum power point operation, and we know how to synchronize the converter to the grid using some sort of phase loop loop. Now, it is very important to understand similarities and differences between synchronous generator and converter when it comes to overall controlling of the converter. Now, we have nearly 100 years of experience and knowledge with connecting synchronous generators to a grid. We understand how the synchronous generator works. A lot of things we take for granted because we know how the synchronous generator works. So some of the key points, the synchronous generator has rotating mass that stores kinetic energy. For example, if we have a 100 MVA synchronous generator with a typical value of inertia constant, say 4 seconds, at rated speed, it generates 4 times 100, which is 400 kilojoules. Another advantage of synchronous generator generator is it can handle large currents during a fault. For a short period, it can handle large currents. And high inertia makes frequency to be more robust because with small change in speed, it can release or absorb energy because of the large inertia. On the other hand, control of power is slow because uh, power is generated using turbines, steam turbines or hydro turbines, and there are time constants associated with the control of those turbines. On the other hand, the converter has no rotating mass, so that's a negative aspect. There's no stored kinetic energy, but there are capacitors in submodules and they can store some amount of electric energy in the electric field. Current rating of the converter is much smaller, so when we're designing a controller, we have to make sure that the current is within the rating of the converter. Even the short-term current rating is not as high as the synchronous generator. And the frequency is more sensitive to disturbances because there's no inertia in the system. But on the positive side, the control of power is very fast because it's controlled simply by controlling switches. Now the challenge of connecting a converter to the grid becomes, converting, connecting a converter to the grid becomes more challenging for weak grids. So what is a weak grid? Weak grid has high input impedance. That means voltage is more sensitive to disturbances and has a smaller margin of voltage stability. Weak system has less inertia, so frequency is more sensitive to disturbances, and a weak grid has less damping. That means if there's an oscillation, it takes a long time for the oscillation to uh, decay and disappear. Now, as I mentioned, engineers are very comfortable with synchronous generator characteristics. We understand it. So one natural tendency to control the converter is to say, okay, let's try to control the converter like a synchronous generator. That means, although there is no rotor dynamics, we can introduce rotor dynamics using equations by modeling differential equations. We can mimic the active power transfer equation and reactive power transfer equation all in software. So the converter will behave like a synchronous machine. And a virtual synchronous machine has the other advantage. It can be implemented using a traditional PLL. And of course, we have to remember that when you mimic the synchronous generator equations, that itself is like a phase loop for synchronization using those equations. The disadvantage of doing this is, although we are informed because we know how the synchronous generator performs, we also introduce negative things that synchronous generator brings along, like electromechanical oscillations. One can argue that with synchronous generator, the inertia is a constant. We can't change the inertia. The mechanical damping is constant. We can't change. But in the virtual synchronous machine, everything is software, so we can change the inertia by changing a value in the software. That's true. But still, we are controlling the converter like a synchronous generator. Now, to test various control techniques within our group, we came up with this simple system. We have bus 1 with a strong bus with a voltage source. Between bus 1 and 2, we have 2 lines in parallel. In this diagram, we show only one diagram. The idea is when you have 2 lines, it's a strong system with short circuit ratio of 4. And when one line is stripped off, we get a weak system and short circuit ratio is 2. So in this case, we want to look at the stability of a converter. So we have connected the 500 MVA converter, and we also have a relatively smaller synchronous generator connected to the same grid, 100 MVA, and we have a load, and we apply a 3-phase short circuit. Now we can replace the converter with the synchronous generator and perform the test and then compare the behavior of the converter by having the converter in the system. And the converter, I don't want to go into the details of the converter because of the time we have. Important thing we need in controlling a converter is how do we control the current, because we know the current in the converter has to be maintained within the rating of the converter. So the three diagrams I have shown, I have on the horizontal axis the direct axis current or the in phase current, and IQ is the quadrature current. And the actual current through the converter is the square root of ID squared plus IQ squared. That means we have to operate inside the circle or on the circle. Your controllers can demand or come up with desired value of ID and IQ that leads to a point inside the circle or outside the circle. And the challenge is, what do we do if the desired ID IQ results in a point outside this circle? So I'm showing three different approaches here. On the left, if the desired ID IQ is on any point on this red arrow, you simply join that point to the origin and get the point of intersection between that line and the circle. Uh, then you can bring the current to the rated value. So in other words, you maintain the ratio between the desired ID and IQ and scale down the magnitude to bring the total current to the rated value. The one in the middle, if the desired current is outside the circle, you simply bring it down, meaning you maintain the desired direct current or the in-phase current and at the expense of quadrature current. One on the right is the opposite. You maintain the desired quadrature current at the expense of in-phase current. And for recovery of the converter from a large fault, we found that the IQ prioritization, the third one on the right, works best. Now, let me introduce the new control technique that we propose. We published this paper in C. Gray Journal of Science and Engineering, October 2019. What we do is we combine the advantages of synchronous generator and advantages of the converter without going into modeling or mimicking the mathematical equations of the synchronous generator. Essentially, we look at how the synchronous generator stores kinetic energy during the fault and then how it releases, and we try to mimic that energy transfer characteristics rather than dynamic equations. So this technique is applicable for weak systems. We have tested it and proved it stores energy in submodule capacitors. To give you a very quick idea of how we do that, if you have 100 capacitors connected in series to get a certain voltage, now if you suddenly decrease it to 50, each capacitor will be charged to double the value. The stored energy in the capacitor is proportional to square of the voltage. So you can see by reducing the number of submodules by maintaining the same DC voltage, you can increase the energy storage in submodule capacitors. And then we try to release that energy in a way similar to how a synchronous generator releases energy during the recovery of the fault. By doing that, we do not introduce electromechanical oscillations. Unlike virtual synchronous machine, we mimic the equations of the synchronous generator. So along with that, we bring electromechanical oscillations. So this is the synchronous generator behavior in that test system I showed. And for the weak system, if we use generic controls for the converter, it goes unstable, so totally uncontrollable. for that test system. So I'm not showing that those waveforms. But if we use the proposed technology, you can see it's stable. And important point I want to bring is the energy. What we are trying to do is we are trying to get the submodule capacitors to store energy in the electric field, just like how synchronous generator uh, stores kinetic energy during the fault, and then how it releases. So you can see the green curve doesn't store any kinetic energy, doesn't store any energy in the submodule capacitors because we use the generic controls. Blue curve is a synchronous generator. So during the fault, it absorbs kinetic energy, increases speed, and absorb kinetic energy, and then it releases after clearance of the fault. And the yellow curve, orange or whatever, is the converter with tune controllers using the proposed technology. So you can see we try to, with tune controls, it somewhat replicates how the synchronous generator absorbs energy during the fault and releases. So uh, the essence of the proposed technology is we don't try to mimic the differential equations of the synchronous generator, but we identify that the reason why synchronous generator is so successful in recovering from fault is because it can store energy and release after appearance of the fault. So we mimic only that part using proper controls. There are a lot one can do to improve this method or get some ideas from this approach and come up with even better ways of controlling a large scale solar PV installation. So that's all I have for this presentation, and I'm sorry I took much longer than I was supposed to. And I'm happy to answer any questions.
Thank you very much, Professor Udaya Annakkage. I'm Madhushika Munasinghe from IEEE PES Student Branch Chapter of University of Moratuwa. Now we are moving to the Q&A session. Participants can direct questions either through the chat box or using the option raise hand. When you raise hand, I will call upon your name and you can unmute yourself and ask the question. Also, we have a small request from the participants. We have shared the link for the feedback form in the chat box. Please spare a few minutes and give your feedback about the webinar. We have one question from participants. What are the solar grid integration challenges?
Okay, that's a very good question, and I was trying to touch on that. I will elaborate it now. Thank you for giving me the opportunity to elaborate on that. You know, at the end of the presentation, I looked at the chat box and I saw that I have been asked to take time. I didn't see that, so I rushed the presentation. So the challenges of the grid integration, as I said, when you connect the uh, solar power plants, are usually remote from urban areas and remote from power grid. So the nearest point to which you can connect may be far away. That means the point of at the point of coupling for on the AC side of the grid, AC side of the inverter, is very weak because of the transmission. In the test system I showed, the weakness of the grid was because we had two parallel lines and one tripped off and created the weak. But in reality, if the solar power plant is far away, the AC side of the inverter always weak. And with weak systems, if we are using a PLL to synchronize the converter to the grid, uh, tuning of the PLL is one of the biggest challenges, choosing proportional and integral gains of the loop, and the best values of KPKI, proportional and integral controller gains. The best values of those are not the same under different operating conditions. So how do you come up with a set of values that are robust to the range of operating conditions? The other challenge is with weak grids when there's a three-phase or any severe fault condition, recovering from the fault. And we know there are grid codes that says must satisfy low voltage right through. That means it should be able to survive severe fault for a given quite time period, and it should cover the voltage of the uh, inside of the inverter according to a certain rate, and it should settle within specified in the grid codes. And with the weak grids, it's a challenge, and as I explained in my presentation, although very briefly, uh, virtual synchronous machine approach is the most talked about approach, and has problems. So those are the main challenges, and those challenges are always opportunities for people to come up with new ideas, contributions to the technology. And as I said at the very beginning of the presentation, one of the reasons of choosing this topic, I think in Sri Lanka there's enough knowledge base and expertise to make contributions. So I hope I answered that question. If I haven't, maybe you can type your question. I will move on to the next question. Do capacitors use a virtual inertia for solar plant? Again, a good question, and I like somebody asked this question. I wouldn't call it uses inertia. Inertia, if you look at the dictionary meaning of the word inertia, inertia is your resistance to change. You don't want to change. So with rotating synchronous machines, uh, we have the inertia because can't speed up rotating mass quickly uh, because of its inertia. But with capacitors, you don't have that problem. So with capacitors, what we do is would use the term stored energy rather than using inertia. I hope I answered the question. Why does the voltage vary? But voltage variation is not because of the solar power plant, it's on the network side. When there's disturbance, sudden addition of load or drop of load, or tripping a transmission line, changing the topology of the grid, all these things can create changes in voltage in the network. And, and this sensitivity of voltage to disturbances is high for weak systems. So it is not the solar integration that creates this, is on the network side, but the controllers in the solar power plant must be able to withstand these variations. Uh, the controllers make the solar power plant unstable, then it's not good. So, that's the reason for high level diagram of control. I only showed maximum power point tracking and in-phase component, the current control in the in-phase component. we can also have also have a temperature component control. With that, we can control can try to control the AC side voltage of the inverter. And of course, that means you are injecting reactive current. Converter current capability is strained. So if we are not injecting a lot of active current, then we have margin for, especially during the night when there's no solar energy generation, you can use the full current capacity of the converter to support reactive power. No in-phase component of current, so full capacity current rating can be the reactive current. That means you can control you can serve as a voltage regulator. The next question.
Excuse me, sir. There's someone raising
Yes.
their hand. Shall we
Okay.
go on to him and
Yes.
then answer?
Sure. Yeah,
Okay,
please.
thank you.
Yes, please.
W.D. Prasad, can you please unmute yourself and ask your question?
So this is Prasad. Thank you for your presentation. I had just a quick question. Now, these days, people are talking about this virtual inertia control in these techniques. So as you think, how practical the use of that technology in these cases, especially in terms of the security of the system?
Well, again, virtual inertia, I discourage people using that terminology because it's not the inertia that we want to uh, offer to the network. It is the stored energy. It is the stored energy that plays the big role in uh, making a good contribution from the converter to the stability of the network. Inertia, uh, positive aspect of inertia, having high inertia is system frequency is not very sensitive to disturbances. If you have high inertia, the speed of synchronous machine won't change much when it releases extra energy inertia. So that's one aspect. For frequency regulation, inertia is good. But for recovery from a fault, it is not the inertia aspect, it is the energy storage aspect of the synchronous generator. That's important. And uh, people associate that with inertia, which is in very loose terms, that's okay. But one has to understand the physics behind and see what really helps uh, contribute to the network. It is the stored energy. So uh, mathematically, you can write equations and use that in your controllers to mimic inertia, but uh, you have to have real energy storage, physical energy storage to make an impact. So you can do that on using submodule capacitors as we explained, or you can have separate energy storage, battery energy storage along with your solar power plant to store that energy and release the energy when it is needed. Uh, so Prasad, did I answer your question?
I think so, sir. Thank you.
Hey, nice to hear you.
Yes, thank you, sir. Yes.
That was my student.
Thank you, sir, for your explanation.
Okay. Can I move on to the next question on the chat box?
I think so.
Okay. So the next question is the proposed technique practically applicable for large-scale solar power plants only? The voltage level at PCC matters. Most appropriate voltage level to apply such a technique. No, the technique, uh, there's no constraints on what voltage level. It applies equally to any voltage level. And I encourage anybody to do more research and come up with better ways of doing this. Of course, you can add on top of that, you can add damping control, you can add frequency regulation to come up with more comprehensive controller using this. And one thing I should mention is when you're designing the inverter, you have to make sure that the voltage rating of the capacitors are higher than the voltage rating of the capacitors conventional control. The next question also comes from one of students, past students, Charitri. Controller interactions with the grid, stability. Controller interactions, it won't affect the stability of the solar power generation side of the solar power plant, but the controllers, since they are power electronic switches, controllers can interact at high frequencies, especially if there are resonant frequencies in the network. Can have network resonant frequencies if there are series compensated lines, L and C type electric resonance points, and it is possible that the converter can have high frequency interactions. I know industry has reported with the full scale converter connected to the grid, some high frequency interactions, several power plants in China. So it's possible. How does multi-junction photovoltaic cells? I must admit that my expertise is not physical electronics. Question is valid, question is very good. I don't pretend that I know physical electronics enough to answer your question. So I'm sorry. Next question. For electricity grid like in Sri Lanka, is it feasible to implement only domestic solar power systems without any large scale? Well, domestic solar power integration is good with two-way structure so that people can sell electricity to the grid. Good for the economy, overall economy. But I think Sri Lanka needs large power plants. I know there's a big shortage of power, if I understand correctly. Shortage of power, and only option to come up with large power plants is go for fuel-based generation. In my own personal opinion, I think Sri Lanka can and Sri Lanka should go for 100% local energy independence from external countries. I think Sri Lanka can do this sort of solar and wind potential. No more questions?
Sir, I have one more question. Sir, in your presentation, you explained that I think that's some of your work, that there were no electromechanical oscillations kind of things I remember something. So
Yes.
what the question I have is now, can you a little bit further elaborate that now when in the presence of these solar systems, how that can impact on the power system oscillations? Will they introduce, will they worse, or what will happen?
Okay. Now, to answer this question, I will excuse from other participants because I want to explain this in a, I know Prasad understands what I'm going to talk, so I'm going to explain at that level. So if some of you don't understand, I request you to bear with me. So Prasad, if you mimic the differential equations of the synchronous generator, you mathematically model the swing equations. And when you have swing equations, it creates electromechanical oscillations. In this case, although there's no mechanical, mathematically you introduce those two differential equations into the system. And as you know, it will create two additional modes into the spectrum of modes of the oscillations. And also we have controllers, and controllers have, if you have PLL, it has two differential equations. That means two state variables that will lead to two additional modes of oscillation to the spectrum. And we have various PI controllers, slow control of the outer loop and fast control in the inner loop controls to control D and Q components of the current. So those are fast controllers, and PI controllers used in those controllers introduce additional differential equations and additional modes. So it all depends on the gains used in these controllers. If you go a little bit more into details, Prasad, we can combine all these equations and come up with state space and calculate eigenvalues. And we can look at the eigenvalues and participations of state variables into modes to see these interactions. And if the network has series compensation, we have, and of course, if you want to model those frequencies in the network, you can't use conventional constant admittance type modeling of the network. You have to go into dynamic network modeling. So with that, you can see interactions between the controllers and the network. And also if there are other dynamic devices, like another converter connected to a nearby bus in the AC system, you can have interactions between the controllers of the two nearby converters. So all these things you can analyze using eigenvalue techniques, and you can avoid those situations also using eigenvalue techniques by tuning in the gains of the controllers to eliminate, or even if you can't eliminate, you can make those oscillations well damped. So the disturbance excite this mode, it will be damped out very quickly. I hope I answered the question. Probably I went too much because I know Prasad understands what I say, so I wanted to go a little bit further.
Yes, sir. Yes, I got the point. Thank you.
Sir, can I ask a question? I'm Charitri.
Yes, Charitri.
Sir, as far as what I've read, I have seen in most of the literature and in the secret brochures, they're talking that these control interactions when we integrate solar and wind plants, they go from electromechanical range to electromagnetic range. So what does that has to do with this stability, fault recovery and all these things?
I muted my. Charitra, I missed your question. Can you kindly repeat it?
So in some of the recent research, they're talking about some control interactions with the grid, and they range from the electromechanical range to the electromagnetic range. And they talked something about negative damping, which they have modeled using this eigen value analysis as well. So does this affect the control and the stability of integration of a solar plant?
Theoretically, it's possible because the converter has low outer loop controls and fast inner loop controls. Low outer loop controls can contribute to low frequency oscillations against other dynamic devices in the network. So this is theoretically possible. I don't remember coming across any industry experiences, utility experiences of low frequency oscillations between inverters and the grid. But as I said, theoretically it's possible because the converters have low frequency, converters have slow controllers in the outer loops. Did I answer your question sufficiently, Charitri?
No, that's it's more than enough. Thank you very much for your explanation.
I would like to add something non-technical, if I may. In the introduction, when I was introduced, I don't know if anybody noticed, my first degree was from U of M, with M being Moratuwa. My master's also from U of M, but M is Manchester. My PhD also U of M is Manchester, and I work at U of M. That M is Manitoba. I wanted to.
That is interesting, sir.
Funny aspect. Questions, comments?
I think we don't have any more questions. So that brings the end of the webinar today. Thank you very much, Professor Udaya Annakkage, for joining us today and the valuable insights shared. It was a wonderful session with a lot of knowledge sharing. And also,
Thank you for the opportunity, and I wish all of you very successful career.
thank you very much, sir.
Sir, this is Lidula. Thank you very much and very happy to see you. Thank you for your time and all the explanation.
Yeah, nice to hear from Lidula, Prasad, Charitri, all past students of U of M, U of Manitoba.
Thank you very much, sir.
Okay, goodbye. All the best and stay safe.
Stay safe, sir. Thank you.
Don't get caught into the second wave.
Yeah, sir.
Okay,
sure.
take care, everybody.
Take care. Bye.
And also, as the organizers, we are grateful to Engineer Kalana Dharmapala for contacting Professor Annakkage for the webinar. Our special thanks goes to Dr. Lidula Vidanagamaratige, the advisor of IEEE PES student branch of University of Moratuwa, for the support given in organizing the webinar. Thank you very much, everyone who has participated today. And also, please give your feedback for our webinar by filling the Google form we have shared in the chat box. Please keep in touch with IEEE PES Student Branch Chapter of University of Moratuwa to our future activities. Once again, thank you all for your participation. Stay safe. Good night.